Okay, hi everyone. Welcome to another episode of Science and Technology Q&A for kids and others. All right, I think we have a few questions that were left over from last week. There's a question from the chemist here. If humankind had evolved 12 fingers, and if we all used base 12 to count and to do commerce, would this have made any difference to our scientific development? Okay, let me hold on. Just trying to organize my screen here a little bit. There we go. Interesting question. Never thought about that before. Well, let's talk about a little bit of history. So the first sort of civilization that really, at least that we know about, that really developed numerical kinds of things in a very serious way were the Babylonians about 4,000 years ago. Kind of the first time there'd been serious cities and things had to be organized and people needed records and they needed to have ways to decide about commercial things and taxation things and all those kinds of things. The Babylonians used base 60. That's how we ended up having 60 minutes in an hour, probably also 60 seconds in a minute. They had a somewhat more elaborate version of questions like how many days in a year, things like that. But they had a base 60 system, and they knew about lots of kinds of things in math. Actually, we just recently sort of finished off doing some math exercises that were on one of these Babylonian tablets from maybe 3,000 years ago that were presumably school exercises at that time. Sort of latest technology. I think back in the day, probably the Babylonians could only work out the answers approximately, but we can now do it exactly and so on. But in any case, the Babylonians knew about lots of kinds of things. Some things they didn't know about. For example, they didn't know about decimals. So numbers, 2.7564, et cetera, et cetera, et cetera. They didn't know about that idea of having fractional parts of numbers like that. Instead, all they knew about was ratios of numbers. So they would say, it's 2 plus 1/60th or 2 plus 2/60ths and so on. And that's a perfectly good way to deal with numbers. It gives you a little bit of a different idea about which numbers are important relative to numbers like decimals, where it's like you can put any sequence of digits after the decimal point to get to specify a number. So for example, the Babylonians had this way of doing things with base 60. They were very concerned with reciprocals, 1 over certain numbers, how that could be expressed. The Egyptians, I think even more so, there are these things that these days get called Egyptian fractions, which is, can you write a number as something like 1 over 2 plus 1 over 7 plus 1 over 9 plus whatever? You can write any number like that as a sum of reciprocals. Actually, there isn't even a unique way to do it. There can be several ways to do it. And that's a different way to write numbers. And it's kind of one of the issues is you say, well, there isn't a unique way to do it. And that's a troublesome thing in terms of dealing with numbers. If you've got two numbers and somebody hands you, one of them is represented in terms of 1/7, 1/19, 1 blah, 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 and another one is represented some other way, and you don't know, those numbers don't look the same. So you can't immediately tell those numbers are the same number. Whereas if you have decimals, 1.27642 or whatever, that particular sequence of digits, that represents a particular number, and there's only one way to represent that number. Well, actually, little footnote there, which is very important for mathematics, higher mathematics, is the number 0.999999999 going on forever is really kind of the same number as 1.00000. There's when you make that sequence of nines as infinitely long, it's like you're infinitely close to the next number up, which is 1.000. And that identification of numbers like that causes all kinds of issues in higher mathematics. But in any case, back in Babylonian times, the idea was it's rational numbers, ratios of things, ratios to something over 60 and so on. That was the story all the time. So for example, when they made square root tables, some numbers, one of the discoveries often attributed to Pythagoras, is the discovery that that something like the square root of 2 cannot be written as a rational number. You say what, when squared, when multiplied by itself, is equal to 2, the answer is 1.414, blah, 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 infinite sequence of digits. There's no way to write the square root of 2 as a ratio of two numbers. It's not equal to, 11/7 or something. It's a number that cannot be expressed as a ratio of two whole numbers. And that was a discovery that is said to have been very disappointing to Pythagoras, because he kind of had this idea that in the world there should only be these nice ratios of things, but yet square root of 2, which is something easy to construct, didn't have that feature. Well, when the Babylonians made square root tables, because they only had rational numbers as a way to represent things, when they got to a number that couldn't be expressed in terms of rational numbers, they just left that space blank in the square root table. So they didn't have a way to express it. So that's sort of a downer to the idea of everything is represented as a rational number. When you have something that isn't, it's like, how do you express it? You don't have a good way to express it. The idea of decimal numbers, or this idea that you can have numbers after a decimal point, that works even if you're using something other than base 10. So normally we just use 10 digits, comes from our 10 fingers. I think the question here was about, what if we had 12 fingers? We might use base 12. We'd be counting, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then instead of going to 1, 0, we would go after 9. We'd probably have something in modern hexadecimal. It's usually A. Then that would represent a digit for 10, a digit for 11, and 12. What we call 12 would then be 1, 0 in base 12. So, but in any base, you can have this idea of writing fractional numbers as point, and then then successive 1/10th, 100th, 1,000th, etc. That could be 1/12th, 1/12th squared, 1/12th cubed, and so on. But that idea of decimal numbers, which seems completely obvious to us now, of numbers with decimals, numbers with decimal points and so on, that idea didn't arise until the beginning of the 1600s. So it was that idea, even though people have been using numbers for thousands of years and had worked out all kinds of mathematics around numbers, the idea that you could write out a number as the sequence of fractional digits like that didn't arise for a long time. There are other ways to represent numbers other than the ones that we use. So we normally use positional notation, a number where there's a units column, a tens column, a hundreds column, whatever. Instead of using base 10 for positional notation, we could use base 12, where we'd have, 1, 12, 12 squared, 144. I don't know what 12 cubed is. I'd have to work that out. We can also, computers like using base 2, where the digits are just 1 or 0. So there's the units, then the 2's column, 4's column, 8's, 16, 32, et cetera, et cetera, et cetera. These are all notations for numbers that are basically use a number is equal to some sum of powers of some particular thing. But there are other ways to represent numbers. One that's a little bit elaborate, maybe I won't explain it in detail, is a thing called continued fractions, where you say that a number is 1 over, 1 plus, 1 over, and it's a big, long, you show it write it down. It's kind of fun to write down because it's a very built-up fraction of many, many layers of built-up fraction. Continued fractions have all kinds of nice properties about the ways that you can do arithmetic with them and so on, and the ways that that numbers combine with them that are much better than what you get with positional notation, where you have to have all kinds of carry digits when you do arithmetic on them and so on. So anyway, I think this question about sort of how you represent numbers and is that important in the development of science, there definitely are ways that this can have an effect. I'm not sure about base 12 versus base 10. That one's less clear to me. I'll give you an example of an interesting piece of science history related to the representation of numbers. So back in Roman times, numbers were represented with the Roman numerals. And The Roman numerals are things like, there's a big I for 1, there's a big V for 5, there's a big X for 10, all those kinds of things. And one feature of numbers at that time is numbers were represented by letters. Same thing was done in Greek numerals. Greek numerals, they actually used this sequence of letters in their alphabet, alpha, beta, gamma, etc., as 1, 2, 3, etc. But in any case, the basic point was numbers are represented by letters. Okay, so then let's say you're going to try to do something like algebra. In algebra, we're used to using letters to represent variables, unknowns like X and so on. Well, they kind of didn't have a way to do that because they kind of didn't have the idea that you could distinguish numbers from things standing for numbers. It's pretty obvious to us today, but that wasn't an obvious thing. And the fact that they had numbers that were written in terms of letters kind of really slowed that down. And it was only when Hindu-Arabic numerals came to the West, basically around 1200 AD, that this idea even could emerge of being able to have letters that stand for numbers. And it was in the 1400s, Vieta and people started inventing algebra and had this notation for variables standing for numbers. I think it was Descartes who in the 1600s, who introduced this X, the ubiquitous, X is the unknown variable. He'd been using, from the early part of the alphabet, ABC, he'd been using those letters to represent fixed things. And then he was like going from the other end of the alphabet to represent variable things where you didn't know what the value was yet. And I think it's said that back in those days, that when he was getting books printed and so on, that Z's, at least in France and the places and the parts of Europe where Descartes hung out, the Z's were very uncommon. And so if you wanted to get your book printed, the printers would be up in arms. They'd say, we don't have any Z characters. What are you using all these Z characters for? So he decided not to use, even though he had this kind of idea, use the end of the alphabet to represent unknown things. He decided, stay away from the Z's. There aren't enough of those. That printers, just to explain this point, back in the day, right, printing was done by having little pieces of lead that were in the shapes of letters that you would assemble in rows, and then you would use that as a thing to actually print your book. And so it mattered how many physical Z's or X's or something had been made. They were usually in these wooden boxes. In modern times we talk about uppercase letters. That was because there used to be these two cases, wooden cases, that the uppercase had the capital letters, the lowercase had the small letters. And that was how you would do typesetting, by pulling out these pieces of lead type. Okay, how do I know this? Well, because when I was a kid, that technology was still extant, and I even used, I guess it's called letterpress these days, the small press things. In my early, as a high school kid, and my early efforts at advertising things often involved making printed flyers, which I would print using that kind of letterpress, printing press thing. And you actually had to take the pieces of lead type and arrange them in these little trays. And it's always fun to see that the E's box of type was always bigger than the X's box of type, because there are more E's in typical English than X's and so on. But anyway, that's the little bit of the origin of the X for the unknown variable. All right, we have lots of interesting questions here. Okay. It's a question from Parmenides asking about Dana Scott and looking forward, looking backward. That's interesting. I literally just interacted with Dana this week, so that's a interesting thought. Okay. Gosh. All right, lots of questions here. There's a question from Hipposu. In our physics project, we imagine that the universe emerges from a simple set of rules. The question is, could the legal system emerge from a simple set of rules? Interesting question. I think the answer is no. Let me try to explain. In physics, what we say is there's some little rule, and you apply the rule, you apply it again, you apply it again. The rule is building something. It's generating a thing. Maybe it's generating our whole universe. That's one sort of way you can use rules. The other way you can use rules is as constraints to say, this is what should happen. We'll only allow things to happen when they follow this rule. That's more what happens in mathematics. In mathematics, it's often you're given a set of constraints. It's this thing obeys this equation. This thing has this property. Then what can exist that has those properties? So in other words, in kind of the way we think about the universe in our physics project, it's like, given these rules, just run the rules and build something. Whereas in doing mathematics and in the legal system, it's more a question of, we've got these rules, rules constrain how things can work. Okay, so the question then is, what's the interplay between these things? Can you have, if you want the world to be a certain way, can you write down constraints that for which will make the world be just this way and not another way, not some way that, oh, we didn't think of that, we didn't want that. In other words, can you have a simple set of constraints that leads to the outcome you want, that sort of force the outcome you want? Well, the answer is it's really hard. And let me explain why. The reason is, in this, you just generate everything from rules. You can start with these very simple rules, and you can end up producing very complicated behavior. You can generate behavior that sort of seems irreducibly complicated. You know, you might think you start with simple rules, you'll always get simple behavior. Well, you don't. You can start with some simple rules and you get extremely complicated behavior, which is kind of what we think is happening in the universe. We have these simple rules, yet we have the whole universe with all the complexity that the universe shows. So then you say, well, I want to, for example, let me give a practical example. I want to build an AI, an artificial intelligence, and I want to give that artificial intelligence ethical principles. And I want to tell the artificial intelligence, operate in these ways and not others. I want to give you constraints on how you should operate. That's similar to the operation of the legal system, except in this case, it would be, because it's operating on an AI, it's not sort of telling people what to do. It's having an AI that has a code inside it, which it will just follow, that it's a little bit better defined. So you can say, okay, you know, what do you put into the AI to make it work the way you want it and not any way that you might not want it? Okay, so the problem is that it is kind of an inevitable feature that, you know, you put in these constraints. You say, I want it to do this, I want it to do that, I want it to do the other thing. There is no, and a little bit harder to explain, but basically to force some particular form of behavior that where, okay, if the thing is operating in a world where there is computational reducibility, where complicated things can happen, it is inevitable that there is no simple set of constraints that will always ensure that sort of nothing unexpected ever happens. How to explain this? I mean, in a sense, it requires going into a little bit of kind of the foundational theory of computation and a bunch of things I've figured out at various times to explain just how this works. Let me mention an analogy. In the mathematics case, one of the things you might want is say, maybe 130 years ago, people said, we're going to write down a set of axioms which are going to define how numbers work. They're going to define arithmetic. They're going to say, for all numbers x and y, x plus y is the same as y plus x. For all numbers, blah, 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 this and this and this is true. Okay, so there's a set of axioms that you might say describe features of numbers. Well, what people originally thought is, there's a set of axioms and they describe numbers. Nothing can exist in this sort of artificial world except the numbers that we're used to, whole numbers, whatever else. Okay, well, that all looked good until 1931, when Kurt Gödel came along with his Gödel's theorem idea, in which he showed that basically what you got by these axioms, you could never constrain yourself to get just the integers, just the whole numbers, and nothing but the whole numbers. That if any finite set of axioms would always have the property that there would always be some unexpected thing that was also consistent with those axioms, some unexpected consequence, something that, yes, it officially obeys those axioms, but it doesn't really obey them. So that's a feature of Gödel's theorem, that in addition to ordinary integers, there can be so-called non-standard arithmetics, which are incredibly weird, but nevertheless still obey those axioms. You can say, let's patch it up, let's add more axioms, let's try and make it so that we're constraining things more. Well, you'll never be able to do that with any finite number of axioms. Okay, so fast forward to modern times, and I'll give you an example of how that manifests in practice. So there's a blockchain called Ethereum, which is a cryptocurrency, a purely digital currency that operates according to a certain set of rules that are encoded in basically programs. Well, a couple of years ago, 3 years ago now maybe, there was an attempt to have an investment fund that was going to be based on Ethereum. And there was something called the DAO, not the DAO, D-O-W, not the DAO, D-A-O. It was an attempt to make something that would be a distributed autonomous organization. It was an attempt to make something where the laws, the rules for this organization, the legal rules for this organization were purely defined in code. There was no human was going to be involved. Nothing was going to be there except the code. And seemed like a good idea. Seems like what could possibly go wrong? Well, what went wrong is somebody found a way to use the code that was there to pay themselves $50 million. And everybody said, you can't do that. That's not what, this was an investment fund for investing in whatever. You can't just pay yourself $50 million from it. But the person, I think, said, well, look, it's just, it's all operating according to code. And what they did satisfies the constraints defined by the code. So, well, but that wasn't what the intent of the code was. Well, but that's not what the point is. You're saying, is there a set of rules that you can write down that's just in the code that represents what should happen? Well, in the end, what happened was that there was sort of a fork made of Ethereum in which the set of people, some people said, we're just going to ignore the fact that we said everything was going to operate according to code. We're just going to come in and change everything ourselves just by hand. And other people said, no, let's let it operate according to the code. And this person will run off with some money that they shouldn't have otherwise. We don't think they should have, as humans should have had, but the code said they could do it, so it has to be okay. I think, I haven't looked recently, but the relative value of these two forks, the one where people just came in and changed it, was vastly more valuable than one where they just let the code run. So that's a sort of practical example of the attempt to sort of write down essentially computational rules that say how the world should work. In the end, this question of, can there be a simple set of rules that are sort of the core of the law? The answer is, I don't think it works. I don't think that a thing where you have constraints that produce behavior you want, I don't think you can do that in a sort of finite way. And you see that in legal systems. There are, the US, for example, has a constitution and which is sort of defines the core of its legal system, but then there are endless precedents that get added for specific cases about what do you do if blah, 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 blah. I think it is inevitable. I think it's essentially a mathematical inevitability that you will always have this, what do you do in the case of blah, 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 blah. And there isn't really a kind of a core sort of simple rule that you can give where you just say, follow this rule and all will be good. I mean, this has come up a lot in recent times in things like AI ethics, in questions like, if you're ranking results that people are going to be shown and you're trying to decide, which results should be removed because they're bad in some way or another, what's the rule for doing that? Is there some sort of golden rule that you can use, which is just some simple principle where you just follow that and you work out its consequences and it will be good. I don't think it works that way. I don't think that's possible. I think that in a sense, what is possible is, given a set of sort of human values, you can make an attempt to capture those, but there will always be sort of things that happen in the world where you haven't quite defined how those values will cover that particular case. At least that's my view of it. Let's see. There's a question here from Mahmoud about imaginary numbers and how they manifest in real life and implementing quantum logic circuits. Okay, that's a bit of a challenging one. Let me see what I can do for that. So, okay, so ordinary numbers, the ones we count with 1, 2, 3, 4, 5, people sort of understand how those work. It took a long time in the history of the development of mathematics before people even understood 0 to be a meaningful number. And it was, I think, 1400s before people understood that negative numbers were a useful thing to think about. -1, -2, -3. It's like numbers 1, 2, 3, 4, 5. If you're counting apples or sheep or something, you can have 5 of them. But what does it mean to have -5 sheep? You have to have kind of a bigger story around what you're doing. It's like, well, I owe you 5 sheep, so I count as having -5 sheep. And by the time you're doing these sort of more abstract accounting kinds of things, negative numbers start making sense. When you're trying to solve mathematical problems, they can make sense to introduce. Well, okay, so if we're in the solving mathematical problems, here's a mathematical question. So we can say 2 times 2 is 4, 3 times 3 is 9. Let's say we're given 9 and we're asked what times what is equal to 9. What is the square root of 9? So 9, we can say, okay, the answer is 3, all good. Any positive number, we can say the answer is whatever it is, all good. Okay, what happens if we have a negative number like -1? What, when multiplied by itself, is equal to -1? You think about it, it's like, well, -1 times -1 is +1. So how do we make something where the thing times itself is equal to -1? So back in the 1500s, I guess, a chap called Cardano was famous for having said, in order to, in his particular case, solve cubic equations, we will have to introduce this thing which has the property that the thing times itself is equal to -1. And that thing got called I, and that thing called I is an imaginary number. It's a number that it's just a number that has the property that the thing I times itself is equal to -1. You can build up a whole system of numbers. You can say something like 3 plus I, which is the number 3 plus, or 3 plus 2I. So number 3 plus 2 times the square root of -1. And you can kind of think of the ordinary numbers as being one set of things and the imaginary numbers being another set of things. And we can think about them as, we can draw them as coordinates. We can say along the horizontal axis, we're plotting the value of the real part, and along the imaginary axis, along the vertical axis, the imaginary part. So 3 plus 2I would just be a point in this plane where we're saying we go 3 units along horizontally and 2 units up, and that's 3 plus 2I. Or we could say 1 minus 7I will be 1 unit horizontally and 7 units down in the imaginary direction. So in a sense, complex numbers, which are numbers that have both a real part and an imaginary part, you can just think of complex numbers as being like pairs of ordinary numbers. There's the real part of the number and the imaginary part of the number. Why is this useful? It's useful for a zillion different purposes. It's particularly useful because a lot of equations can be, it's the fundamental theorem of algebra is that a polynomial equation, an equation involving, squares, cubes, whatever, powers of numbers, that says x cubed plus x squared minus 3x equals 7 or something. An equation like that, any such equation can be solved using complex numbers. That is, there exists a value of x that is a complex number where you fill it into that equation, you work out the equation, and the equation is correct. So that's why complex numbers, that's one of the reasons complex numbers show up all over the place, is because they let you solve any equation involving polynomials. There are a lot of other reasons why complex numbers are useful. They're a good way to sort of, when you've got a pair of numbers, often things work out so that you can represent them well as a complex number. And there are rules for arithmetic with complex numbers and so on and so on and so on. Okay, what does that have to do with quantum mechanics? So quantum mechanics is the theory of how sort of very small things work, like electrons and so on. It's sort of the what happens when you're not dealing with large scale objects like marbles or something where you can just see the object and it does a definite thing. In quantum mechanics, you're dealing with what do individual electrons do, and what they do is something more complicated than what large scale objects do. And in fact, in our physics project, we have finally, I think, got to a point where we actually begin to understand how quantum mechanics really works. And what's happening in quantum mechanics is, instead of a definite thing happening, sort of a collection of all possible things happen. Let me give you an example, actually a very recent example, which I've been figuring out how the analogy really works. If you play tic-tac-toe, what in the country I came from, it's called noughts and crosses, game, you know, X's and O's or whatever on a piece of paper. Okay, so you start off, you've got a blank board. You put down an X somewhere, somebody else puts down an O somewhere, keep going, eventually somebody wins the game or whatever. But imagine the set of all possible games. You start off from the blank thing, and you could put the X in any one of 9 positions, then you can put the O in any one of 8 positions, and so on. At each step, there's many possible positions. You can make up this whole graph network that shows you start from this initial condition where it's just blank. You have these 9 choices, then you have like 8 choices from each of the 9 choices. You keep going. It turns out in that particular game, I think there's 5,741, I think that's right, possible configurations of the game, possible ways that you can have put down X's and O's and so on in the different steps of the game. But so in the game, there are all these different possibilities that could happen. That's a little bit like how quantum mechanics works. That quantum mechanics allows you all those different possibilities, but then when we are paying attention to what's happening, all we notice is who won or who lost, the game of tic-tac-toe, so to speak. We don't kind of look inside at all those different paths and how all those paths worked. Okay, but it turns out that the way of figuring out the chance that one person wins the game or the other person wins the game, or in quantum mechanics, the chance that the electron goes this way rather than that way, those chances are conveniently worked out in terms of complex numbers. And actually, you can kind of see a little bit how that might work, how that works. Imagine you have your tic-tac-toe thing, and imagine that you have this network. So you have a dot for every possible configuration of the tic-tac-toe board, and you join it to all the dots, all the configurations that can be reached from that one by one move in tic-tac-toe. And you make this whole network of how that works. Well, it turns out, and in the world of our physics project, it turns out that if you look at kind of the set of all possible configurations that you could have reached after, let's say, 3 steps of tic-tac-toe, you've got all these different possibilities, and that forms what we call a branchial space, a space of branches, because there are all these different branches that you could have taken of doing one move in tic-tac-toe versus another move in tic-tac-toe and so on. And that, so in this, and that space of possible tic-tac-toe moves, you can think of it as being something where all these different possible tic-tac-toe boards, or possible tic-tac-toe moves, they're arranged somehow. How are they arranged? Well, you can think about them arranged in a little bit like ordinary space, but the way that that is arranged is something mathematically different. And it turns out it looks like complex numbers are really important in describing how that's arranged. And in quantum mechanics, the usual description of quantum mechanics deeply involves complex numbers. And we think that's sort of how they arise, is by this description of this thing that isn't an ordinary kind of space that you can kind of move around in like we're used to moving around in physical space, but it's this space of different possible configurations, not actually of tic-tac-toe, but of sort of the innards of what's inside electrons and things like that. But the tic-tac-toe thing is an analogy to that. So the idea in the way complex numbers enter quantum mechanics. When you think about making a computer with quantum mechanics, one of the big things that you might imagine is that you can use all these different paths. Like a standard computer, it's just like you ask it to compute something, it'll just go chunk, 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 and compute to the answer. But if you allowed it to operate with quantum mechanics, you might say, instead of just going chunk, chunk, chunk to one answer, it would branch out into all these parallel threads where it could be trying different things and then hopefully merging them together later. But like, you could be running all the games of tic-tac-toe simultaneously rather than just having your computer just go through, I'm going to do this particular game. So the way that works is you're kind of using this branch hill space. You're having things be at different places in branch hill space, and that all links up with complex numbers. And actually, the mathematics of how this works, we're just figuring this out right now. And it's very cool, and I could get very elaborate and mathematical and talk about it, but let me not do that here. Let's see. Okay. Oh boy, so many questions. You guys are, all right, there's a question from Crow. Is pi irrational because we use the decimal system? Is there a system sort of where it would be rational? The answer is no. There is no, there's no system based on whole numbers where pi would be a rational number. In other words, if we represent a number like we do in base 10, where the number 735 is 5 plus 3 times 10 plus 7 times 10 squared, that way of representing a number by a sum of digits multiplied by powers of the base, if that base is a whole number, we don't get to represent pi like that. And by the way, when you're doing fractional numbers, it's 1 over 10, 1 over 100, plus 1 over 1,000, et cetera, et cetera, et cetera. So with a whole number base, pi cannot be represented that way. Now, tricky thing, if you allowed yourself to use a fractional base, like what if you used the number pi as a base? Well, then obviously you can represent pi. Pi is the equivalent of 10, of 1, 0 in base pi, so to speak. Now, would base pi work out? How would base pi work out? So we could say, well, let's take this number and represent it as pi plus pi squared plus something times pi plus something times pi squared plus something times pi cubed, and so on and so on and so on. Okay, you might say that's a great scheme. Well, okay, here's the problem. Problem is, in base 10, we say we're just going to use digits 0 through 9. As soon as we get to digit above 9, we say that's in the next column, that's a tens column thing. Okay, if we have base pi, we don't get to do that, because it's not like we're saying there's a set of whole number digits that we can use up to pi. We could say 1, 2, 3, and then we'll punt at 3, and then if it's bigger than 3, we say it's pi plus something else, and so on. We don't get to that. There's no, so it will turn out, I'm pretty sure, that there's no unique way to represent a number in base pi. That is, that it isn't the case that there's a unique set of digits that we would give to specify the number. We would have two numbers which are in fact equal. And by the way, if we were trying to represent integers in base pi, they would have infinite decimal expansions. Or infinite pi-eel expansions in base pi, infinite things to the right of the pi-eel point, the analog of the decimal point. But in any case, we would find out that the numbers, for 2, for example, there'd be an infinite number of representations. And so somebody hands you one of these things and says, have you seen this before? You might say no, but actually it's just 2. It's just a different way to represent 2. So there are other ways to represent numbers. So for example, I mentioned continued fractions before. It turns out that some numbers, square root of 2, if you write it out as decimal, it just keeps on going forever. It never repeats. Only the rational numbers repeat their decimal expansion. So square root of 2 is 1.414, dot, 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 dot. You go on for millions of digits. Pi is the same way. It never repeats its decimal expansion. But there are other ways to represent these numbers where you do get a more orderly sort of representation. So continued fractions, square roots are repeating continued fractions, just like rational numbers are repeating decimals. Square roots are repeating continued fractions. Pi is not a repeating continued fraction. Pi has a very weird continued fraction that has all kinds of weird pieces in it, but it doesn't repeat. But you can have other, I think there's a representation involving iterated nested square roots in which pi does have a simple representation. But it's what tends to happen is in any one of these sort of potential representations, you have sort of this trade-off of which numbers get represented easily, which numbers are hard to represent. Is there uniqueness in the way you represent numbers? And when you're doing an operation, how difficult is it to do that operation? How many pieces of the number do you have to update to deal with that operation? Let's see. It's a question from Yagobus. How much do I trust current methods of encryption? Leaving quantum computers aside, are they really unbreakable? Well, so encryption is about, you take a piece of text and you say, I'm going to do an operation on this piece of text using a key. The key might be a password of some kind, and I'm going to grind up this text into something that looks completely random, and it's only going to be ungrindable if you use that same key again, if you know that password. Okay, so how do people do that kind of grinding right now? Actually, I invented a technique for doing this back in the 1980s that is based on very simple computational rule, this thing called Rule 30, where you essentially are generating the key is the initial condition for Rule 30. You generate this sequence of apparently random things that you can use to randomize your text. Well, nobody knows how to break this encryption scheme. Nobody knows how to go from the randomly encrypted thing to figure out what the key was. In fact, if we knew the answer, we would know the answer to some very interesting mathematical problems, which I suspect their answer is can't do it. In fact, I put up a prize recently for anybody who could get even part of the way to answering the question of whether they're either proving that there isn't regularity or finding regularity in the sequence generated by Rule 30. Now, in practice, encryption that's done usually has two stages. There's usually a piece that's so-called public key encryption that's based on properties of prime numbers and so on. And then there's a piece that's usually based on what was really an earlier idea in encryption. So my little Rule 30 thing is a very simple to describe scheme for encryption. You just follow this rule, you get a random sequence of bits, use that random sequence of bits to randomize your message. There are standard kind of encryption things, AES, whatever it is, encryption. There's also standard methods. They're a bit complicated. You look at their specification and what they do is they say, take your message, break it up into blocks, take this sequence of bits in the block, replace it by this other sequence of bits, permute the bits around in this particular arrangement, and then keep doing that a bunch of times. Okay. As a matter of fact, when those methods were originally invented in the 1950s, some of the mathematics was sort of a similar precursor to some mathematics that's been done with cellular automata. It was always very mysterious, actually. In the 1960s and so on, when a particular thing called the data encryption standard was developed in the US, it was always very mysterious. Why was it? It's this weird collection of you replace this block with this, you permute the things around, you do this, you do that. Why? And the so-called S boxes, the substitution boxes of DES, were a big mystery. Why were those S boxes used? Actually, it seems like the mathematics of them came out of mathematics that was done for sort of precursors of cellular automata. And that's sort of why those particular choices were made, but nobody was told at the time why they were made. So, but the current methods for doing sort of large-scale encryption mostly work using these same kind of block cipher substitution permutation type ideas. And they're kind of messy. And do we know for certain that there's no way to be very clever and sort of work backwards in these things? No, we don't. No, we don't. And those same methods are used in, for example, blockchains, where people are trying to do proof of work. They say, find a thing which, when encrypted, gives a bunch of zeros in it. So in other words, you're saying, find something where you find the key, so to speak, so that when you run it through this encryption thing, you'll get a bunch of zeros. And the only way it seems like that can be done is it's a one-way function. You just run it from the input to the output. You can't go back the other way. Can we prove that? No, we can't. It's really not for certain. It's something that people bash at it from time to time, and nobody's managed to crack it, but we don't have a theoretical proof that it's not possible. Now, with public key cryptography, that's not used for very large scale kind of encrypt gigabytes of data. It's used particularly for encrypting doing one level of encryption of keys, dealing with the management of you have part of the key, somebody else has part of the key, et cetera, et cetera, et cetera. That's usually things like 1024, 2048 bits, this kind of length, rather than gigabytes of data. It's not really fast enough to do gigabytes of data directly with that. Public key cryptography is based on, most often on so-called RSA algorithm, is based most often on the fact that it's much harder to factor a number, to say that, I don't know, pick a number, 90 is equal to 9 times 10, than it is, well, let's say 56 is equal to 7 times 8. It's much harder to figure out that 56 is equal to 7 times 8 than it is to multiply 7 by 8 and get 56. And it's believed that the problem of factoring a number is that there's no much faster way to do it than essentially just trying the different possible factors and seeing what you get. Actually, there are ways that are considerably faster than that, but they're not, they don't allow you to just read in the bits of the number and immediately tell you what the factors of the number are. So that's what the security of standard public key cryptography is based on. That problem is thought to be hard, but nobody knows for sure that it's hard. The reason people think it might definitely be hard is it's close to so-called NP-complete problems. So NP-complete problems have the feature that, imagine you have a general computer, any kind of computer. There are problems where if you are told the answer, you can check it's right quite quickly. But if you're not told the answer, you might have to go try a lot of possible answers to see whether it's right. NP stands for non-deterministic polynomial time. And the non-deterministic means you just get to guess things a lot of times and see whether they're right. And so what's believed is that there are problems that have the feature that if you can solve that problem in polynomial time quickly, then you can solve all NP problems in polynomial time. So there are problems known that have that feature. Famous ones are things like satisfiability and the traveling salesman problem. So satisfiability is, given an expression like P and Q or R and not P, et cetera, some logic expression like that, can you find values of P and Q and so on, like P is true, Q is false, R is true, et cetera, so that the whole expression is true. You can certainly find the answer. If somebody shows you P is true, R is false, et cetera, you can substitute those values into the expression you were given, and you can quickly say, oh yeah, I can check that it's true. But to find out whether it's true, you might have to try all the exponentially many possibilities for true, false, et cetera. That's a problem that is known to be NP complete, in the sense that if you could solve that problem quickly, then you could solve all other NP problems quickly. And it's believed that it's not possible to do that. People have tried all sorts of different NP problems and tried to tried to see whether they can crack them and haven't been able to. Now, factoring, the problem which is used as the basis for public key cryptography, is not known to be NP complete. It might be, but it is not known to be. And so even if we could prove that NP complete problems couldn't be solved quickly, we don't absolutely prove that factoring can't be solved quickly. And it's not absolutely for certain that factoring can't be solved quickly. One of the interesting challenges is to make an encryption system that is based on an NP complete problem. Nobody has been able to do that yet. My Rule 30 system, generalizations of it are NP complete. Whether crack them cryptographically is NP complete. Whether Rule 30 in particular is NP complete is not known. But that, and even if something, and the question of whether you can solve an NP complete problem quickly in polynomial time, it's the so-called P equals NP problem in computational complexity theory. And that problem is really hard, and nobody knows the answer to whether that's possible. Actually, some things that have come out of our physics project give a kind of a way to think about that problem that's a bit different than has existed before, where you're kind of thinking about the space of all possible space of all possible algorithms that could do things, and you can sort of represent that as a structure in a kind of space, and you end up with this kind of ball of possible places you can get to with NP, with non-deterministic polynomial time computation, and then specific polynomial time computations are particular threads within this kind of ball of possible places you can get to. And so there are sort of geometrical questions about where you can get that might allow us to make progress on the P versus NP problem. By the way, it's quite possible that the P versus NP problem depends on what axioms you use for your mathematics, whether you conclude one thing or the other. So maybe a very squiggly, complicated thing. But anyway, the original question was, how much should one trust cryptography that exists today? The answer is pretty much. But do we absolutely know from mathematics and so on that it's unbreakable? We do not. Do I think that quantum mechanics is going to make it easier to break? I actually don't think so. That's been a recent discovery from our physics project, because we now understand a lot more about quantum mechanics, so we can say what's possible to do and what's not possible to do. And my guess is that it is not possible to solve NP-complete problems in polynomial time with quantum mechanics, even though there's sort of an indication that at least the factoring problem can be solved quickly, but I don't think it's correct. I think that it's one of these cases where inside the quantum computer, it might know something, but for us to find out what it said will take as much time as it would have taken to do the original factoring problem. It's kind of like, imagine you've got your game of tic-tac-toe and something's happened inside the game, but you don't know what happened until somebody wins or loses. The question is, if you say, well, there are all these parallel games that are going on inside there, well, it doesn't do you any good until you can find out something where you can actually get to the point where you have a definite winner or loser. Let's see. There's a question here about from Rushank about what do I think about AIs writing mathematical proofs? And it says, I read an article recently about AI discovering the heliocentric principle by itself. Look, the question is, what are you trying to do when you write a proof? A proof is in some ways an explanation of why something is true. In order to write an explanation of why something is true, you have to know who you're explaining it to. In other words, there are proofs that I've generated automatically where, yes, the computer has shown that you go from this step to this step to this step to this step, and another computer can easily verify that those steps work. But the story of why this thing is true, computer absolutely doesn't tell us. And there's sort of a separate AI-ish problem, which is to take that set of steps that the computer knows will establish some result and to sort of arrange it so that it is a good human narrative so people can understand what was said. So for example, in Wolfram Alpha, we have these step-by-step solutions, and that's exactly what we've done there. We've made it using AI-ish methods. We've made it so that it generates something which is a reasonable sort of human description of why the particular problem comes out the way it does. But that's a quite separate problem from knowing this is how the answer comes out. Now, in terms of discovering things from data and so on, again, it's really a question of what kind of a story do you want to tell from your data? In other words, let's say you've got data about, oh, I don't know, where the sun is as a function of time in the sky. What can you conclude from that? Can you find a simple model consistent with that, with the path of the sun and so on? Well, that's something where, again, it's very much a question of the eye of the beholder, because what counts as a simple model to someone may not count as a simple model to someone else. And when it comes to an AI discovering that, it's like the AI has to say, look, here are some models that those humans think are simple. Let me see if any of those work for explaining the motion of the sun. And absolutely, you can do that. In fact, that's what statistics has been about for a very long time. For 150 years or so now, we've kind of known how to take sort of general classes of models and say, well, let's see whether they fit this particular thing that we observe. And using machine learning and so on, we can get a little bit more general about what kind of model we use. But the trouble with that is, as soon as we're more general about the kind of model we use, there may be no story about what that model means. So we can say, yes, this neural network, it found a way to reproduce the motion of the sun. Oh, well, it's got 6 million numbers inside this thing. Do we know what that means? Can we tell a story? Can we say that means the Earth goes around the sun? No, that means that we've got a way to reproduce the motion of the sun in the sky, but it doesn't mean that we can necessarily tell a sort of human-based story for this. So it's a tricky thing, asking the question to what extent we can get kind of automated explanations. The bigger part of that question is the explanation to us, not the can you fit the data. Fitting the data is easy, particularly if you allow yourself 6 million parameters or something. It's a question of, can we make a human-like explanation of this? All right, let me do one or two more and then I've got to wrap up here. Boy, there's a question here from someone, Texas Tech, bringing high-end geospatial data analytics to the public in non-conventional educational settings. I think the most significant thing I would say here is check out what we do in Wolfram language with geospatial data. It's really very nice. And it allows one to kind of what we try to do in Wolfram language in general is to provide a language which both humans and the computer can understand. So, you could just say, give me the, use natural language to say counties in Texas or something, and then you'll get back some symbolic representation of that. And you could say, I don't know, you could say, what are the, make a geo list plot of those counties, or make a geo region value plot where you say the population of each county and you put that in. And that's all stuff that you can do in a piece of Wolfram language that is something that people can read. And that's something that's really, really interesting, because it's not like sort of pandering to the low level of what the computer wants to see. It's rather the sort of thing I've spent, the last third of a century doing, is trying to make it so that what one has is something that is sort of clear enough that it can be understood by humans as well as by the computer. And we can represent all of these geospatial kinds of things really nicely at this kind of very high level that's understandable to both humans and machines. And I recommend looking at that if you're interested in a specific place to look to get started. The book I wrote called Elementary Introduction to Wolfram Language has a section about, I forget what it's called, geographic kinds of things. And that would be a good place. It's probably 5 or 6 pages long. It's a good place to start. Let's see. All right, I'll answer one more thing here, which is from Norro. What's the best way to learn something for slow learners? I don't know exactly what a slow learner is. I kind of think it depends on what you're trying to learn. There are things I've tried to learn where I am a super slow learner. And there are things I've tried to learn where I think I learn it pretty fast. I mean, for example, for me, what's a good example? I don't know. There are probably a bunch of kind of physical skills about. I'm not too uncoordinated actually, but things like, what's a good example of something I've tried to learn? Tying a bow tie. I tie a bow tie. I learned that when I was a kid. I used it about 5 times in adult life. But it's things like that. I am, unbelievably slow learner. When it comes to more abstract things, one area I've been learning recently is a very abstract area of mathematics called category theory, and I've been really pretty slow at learning that. Okay, here's the basic point that I found in learning things. So, I learn them relative to things I already know. And there are different styles of learning. So some people you can tell them a bunch of stuff that they don't really understand, and they can kind of swim in that for a while, and eventually they manage to start anchoring things and then they understand it. That's not usually the way I work. I have to build from something I already know, and little steps where I really understand it all the way down the line, so to speak. It's different people learn things differently. I mean, I certainly know people who really do learn things by, first they swim in this kind of soup, and then they start to be able to attach to things. In my case, it's like I really need to know step by step what's happening. For me, also the sort of concreteness of I spent my life building these tools to make this possible. I type some piece of code and something happens and it does what I expect or it doesn't do what I expect. Concretifying what I'm thinking about into Wolfram language code is really an important step for me. That's what allows me, once I have it sort of concretely as a piece of code that I can just run and it does what I think it should do or it doesn't do what I think it should do, then I really feel like I understand something. I would say also for me, explaining stuff is a really good way to know whether I understand it. That's why I like doing these events every week. This is an opportunity for me to try to explain stuff. And every time I explain something, I think I understand a little bit better myself. So I would say that there are different styles of learning things, but I think one question is, do you sort of not learn something because somebody's told you something and then they say, okay, what's the answer to this exercise? And you're like, I don't have the slightest idea. Because you didn't really, there wasn't a series of steps you took where you really understood each step. You kind of tried to jump too far and you end up kind of drowning in this kind of sea of things you don't understand. As I say, for me at least, I find it best to just go one small step at a time where I'm really understanding each step, and where if I don't understand the step, I keep grinding until I do understand that step. Now, it really helps to know about a lot of other things, because the question is, if you're taking these small steps, it's like, where are you starting from? Well, if you already know a whole bunch of other stuff, that's really useful because it gives you a starting point. It's like, in learning category theory, turns out knowing about, I don't know, things about graph theory and things like that, where I can just sort of take for granted I know about that stuff, so therefore I can use it in this other place. I think that another thing that is often what can I say, perhaps downplayed in modern education is just knowing facts is really useful. It's one thing to know principles about how to do things, but you anchor that with just a bunch of facts about all kinds of things. And it's amazing how often I'm using a fact about something that I learned in some area of, I don't know, learning about something about physics. And I'll use that fact in thinking about something about computers, or I'll use that fact about, I'm sure probably even today in the things I've been talking about here, it's like a lot of things are anchored with facts. And even knowing about historical facts, for example, getting some sense of how difficult should it be to understand this thing? Was it something which took 1,000 years of human history before people understood it? Well, then you might be excused for it being a little difficult for you to understand it. Or is it something where this was actually pretty easy, a pretty easy step from something else? Well, then you know what was the other thing it was a step from, and you go back and you try to understand something from that. So I think that as I say, people have different styles of learning. And for me in particular, I'm a very concrete learner at some level. I mean, I end up working on very abstract things, but I get to them in very concrete ways. In other words, I've worked on some very abstract ideas and abstract principles and so on, but the way I got to them is I did computer experiments. I saw this, I saw that, I saw the other thing. I made some connections between these things. And eventually I'm at this, high level of abstraction. But that high level of abstraction was reached in little small steps, always seeing concretely what was going on. Again, not everybody works that way. Some people, I think, are capable of reasoning at this very abstract level intrinsically. Sometimes in my perception, they can be like, they can be sort of living in the clouds, and then they realize there's a long way to fall and there's nothing holding them up, so to speak. And that can happen if you're sort of operating at this sort of very abstract level without some foundation to come from. But I think that's and in terms of, for example, in terms of learning things, I would say that I, for example, am a learning by doing kind of person. So two things. I need to be motivated and I need to actually do stuff. So whenever I've said, I'm just going to learn this thing for the sake of learning it, I have a hard time with that. Whenever I'm like, well, I'm supposed to be learning about this, I wonder about this question, that question, the other question. Okay, let me learn these intermediate steps because I care about this question I'm trying to answer. Even if that's something that you might learn in school or something like that, if there's some kind of overarching, this is where we're trying to get to, this is what I'm curious about. If I'm learning about economics, what will happen if, the US government spends $2 trillion? What consequences does that have? Does that mean, there'll be this, that, or the other? How do I understand enough economics in between to know the answer to that question? So for me, having motivating questions is important. I think that also for me, actually doing stuff like figuring out, okay, then I'm going to figure out, if you do this, you do that. And I'm going to figure out, I'm going to write a little program that does this or that, and I'm going to see what the result is, and I'm going to do stuff. When it's just me passively reading something, I personally am really bad at that. In fact, I'm almost shockingly bad. I have probably 8,000, 9,000 books, and I've looked through all of them, but how many of them have I actually read, page by page by page? Depressingly few. It's not the way that I best ingest information. I kind of look, what's the point? Okay, can I figure out why that's true? Let me sort of do it for myself. Again, not everybody works that way. I think but that's in my particular case. And sometimes what happens when you learn things, for me at least, I'm learning some new area. And for a long time, it'll be like every new thing I hear about, it's like, oh my gosh, another thing, I didn't know about that. Oh my gosh, I didn't know about that. And it's like I'm drowning in this area, right? Because it's like, I just can't, it's like, you just told me 100 new things I didn't know. And, I can't extrapolate from the things I did know to all the things I'm being told. But then for me, at least, there comes this moment when it's like, yep, I more or less get it. And then it's like, okay, all these pieces start to fit together. And then it's like, okay, somebody tells me a new thing. It's like, yeah, I kind of knew that. Here's how it fits into the things I already knew. I'm good here. That's the point at which I really feel like I understand stuff, and in which I, the other question is, when you do things, do you make mistakes? What causes the mistakes you make? Are the mistakes you make mistakes because you just, you're doing a piece of math and you lost that minus sign? Okay, that's not a very interesting kind of mistake. Or is the mistake because you fundamentally didn't understand what on earth is going on? I remember, yeah, I could name some amusing ones from my youth of ones where I was like, I don't know how this works. I completely don't know what's going on. And, it's where, but one of the things I think I, for example, have gotten fairly good at, and I think it's a useful skill, is to know when you know, so to speak, and to know when you don't know. And it's like there are things where I'll be doing stuff, people will be trying to convince me of something, for our company or whatever else. And it's like, okay, I get it. I know, yes, fine, let's do that. Let's not do that, whatever. And then there are cases where it's like, I know I do not know. And I know I don't know. You can say, make a decision, do this, do that. I know I do not know. And then you have to go try and figure it out. But that's an important way to avoid making mistakes, is to know when you don't know. Now, if you're told this is a timed exam, you've got to write down a bunch of answers on it, and this amount of time, that's kind of a goofy exercise in my opinion. But given that you're going to do that, well, you do the best you can do. I don't know what the right solution is. I think I'm profoundly bad at those things. The last time I did some kind of exam-like thing was probably when I was 16 years old, which is a depressingly long time ago now. And that was before the days of multiple choice. So I didn't, all the stuff, that I hear from people, my wife happens to be one of these people who's really good at sort of figuring out how to kind of figure out, well, that answer can't be right, and that one can't be right, and this one was this, and this one was this, therefore it must be C. And I never developed that set of skills for sort of gaming those kinds of systems. But in any case, I think that this question of when you do a lot of kinds of things, to me, it's important to not make mistakes if I can avoid it. And a huge mechanism for not making mistakes is to know when you don't know. Another thing is to know the types of mistakes you make. Like when I write stuff, I leave words out. That is my disease of writing, is I write a little bit fast. I think a little bit faster than I write, and I just leave words out. And I have to go back, and I'm pretty good at proofreading my own stuff, but it's like, I know I leave words out. So I have to, go through and like, are all the words there? And when I write code, I have long ago learnt the types of mistakes I make. So that means it's really quite fast for me to like, I know kind of a catalog of things that I do wrong, and that gradually allows me, if something's gone wrong, it's like, oh, okay, try these, this might be the things I've done wrong. So those are a few suggestions, I suppose, about learning things. And I think, it's funny because there are things which I learn where it might look and feels to me like I'm a super slow learner. And there are other things, even the same thing later on. It's like there'll be a period when I'm just unbelievably slow and I don't understand anything. And then, okay, I get it. And then zoom, one's off and running. And, then sometimes I can be pretty fast, even compared to people who've been working on those things for decades. And that's always fun. And honestly, the main advantage that I tend to have is just I know a lot of stuff, and that means it's easier to making connections between things and using some fact from somewhere to make a conclusion about something else. That's a really powerful thing to do. All right, I should wrap up here. Thanks for lots of interesting questions once again, and the ones that I didn't get to this week we'll store up and potentially use next week. So thanks very much, and bye.